one more talk. We have one more talk coming up. All right, Heath, let us know what's happening, who's coming up next.
Yep. So we got Def Bram coming up next. He's going to be talking about HTTP request smuggling, which I've always thought is way over my head. And I saw Albino Wax's talk last year about it, and it still felt way over my head. So we got brand new research. I'm excited to see it, learn more about it. And without further ado, here's Def Bram.
Let's get right to it.
Hey guys, my name is Evan Custodio. I would like to thank Ben and others for inviting me here to give a talk on practical attacks using HTTP request smuggling. So let's get into it. So who am I? I've worked as a hardware engineer for about 13 years, specializing in designing hardware for networking, data encryption, and cloud workload acceleration. Most recently, architecting security architectures for FPGAs in the cloud for a rather large chip maker. I'm pretty new to HackerOne and the bug crowd. My first bug I submitted last August, I think it was cross-site scripting. But since November, between HackerOne and BugCrowd, I've reported about 40 triaged request smuggling vulnerabilities rated between medium to critical. So I'd like to take this opportunity to disclose some of the techniques I've used. My interests are low stack integration and protocol bugs, so request smuggling is a great fit. And some of you already may know of me. If not, I am at DefParam on Twitter. You can follow me there. On the agenda for today's talk, I quickly go over and introduce the concept of cl.te and te.cl desync attacks. Then I introduce a little bit on how I've tested and searched for request smuggling targets in general. After that, I discuss the categories of impact on a request smuggling attack. From there, I move on to more practical attack and recon techniques I've done to increase request smuggling impact. And lastly, I finish the talk with two proof of concept demos. These demos show techniques I've used in the majority of my reports to obtain session takeover and the leakage of PII data. So a quick introduction to CLTE and TECL desync attacks and a warning. These techniques may be dangerous, so understand your program and your scope. A lot of the server assets have high traffic scenarios where there's a lot of connections being made. These attacks can affect those connections and can potentially cause a lot of damage, so be cognizant of that. Also, this talk makes the assumption that all of you have sort of a basic understanding of how HPDC attacks work, although I will be covering it in the next couple of slides, a quick intro. But to level set, definitely check out James Kettle's HPDC attacks talk called Smashing into the Cell Next Door that he presented at Black Hat last summer. And also he references a Watchfire paper in 2005 that has a lot of good insight into this area. Definitely check that out. The other thing that I don't cover in this talk is techniques to force desync, malformed transfer encoding, headers and parameters is not covered in this talk, although it is interesting to take a look and figure out more payloads that can cause desync issues onto your servers. So first we start off with the CLTE desync attack scenario. CLTE's reference is shown as cl.te, which is the front end dot the back end. This type of attack, what this means is that the front end will interpret a web request using its content length header, and the back end will interpret the same request using the transfer encoded header. And so here we have an attacker about to access host.com and issues a post request to the login endpoint. And you see in this post request that the transfer encoding header is malformed. It has a character 1 in front of the transfer encoding. So it is ignored by the front end. And so the front end interprets the content length 35 in this request, which encompasses the payload highlighted in blue. When that request goes to the back end actually interprets the transfer encoding header instead, despite it having the malformed character. And when it does that, it ignores the content length sizing of the packet. And shown here, what it parses out of this request is only the 0 and double line end. The rest of the payload, which is this data that has a get to the robot.txt endpoint, is placed on the socket between the front end and the back end as poison. And so when we take a look at that, we now have this persistent connection between the front end and the back end with this poison of robots.txt. And we have a victim coming in wanting to access host.com. And so that victim simply wants to get the /endpoint of host.com and sends its request to the front end. The front end forwards this request down the same connection that's poisoned to the back end. But we see what happens here is that the poison gets prepended to the request, and the backend interprets that the customer wanted to actually get the robots.txt endpoint rather than the /endpoint. And so the response back from the backend to the victim is the data for robots.txt. TECL desync attacks are similar. So the attacker sends a request to the front end with a similar malformed transfer encoding header like this. And the data portion of the web request contains a chunked size payload that has a web request inside. So in this case, it's a chunk size payload of hex 46 to a post of the somewhere endpoint on host.com with a content length of 100. So when that gets, the front end interprets this as transfer encoding, and when that gets forwarded to the back end interprets this as content length encoding. And so all the back end does is it parses four characters out of the payload, which is the chunked size, hex 46, and then the RN character that follows it, which means that the entire payload that follows it, which is the post to somewhere, gets placed on the front end to back end connection as poison. And so when a victim comes to access host.com from the front end, we have that post to somewhere as a poison between the front end and the back end. They make a web request to /get, perhaps with a session cookie of some sort. And then what we see is when that request gets to the back end, the poison actually gets prepended to that, and it gets placed to a post to the somewhere endpoint, and the get request from the customer gets placed as payload to this post to somewhere, which could be potentially dangerous. If that post to somewhere is accessible by the attacker now has visibility to the session cookie that was placed into the web request that was initially sent. Testing for request smuggling can be done safely. In a blog post released by Portswicker, James outlines a clever method to safely test for desync issues without actively affecting neighboring connections. He has released an open source burp extension called HTTP Request Smuggler to help find desync issues on servers in a burp extension. This tool was extremely helpful and useful on getting started with my desync detection recon. However, personally for me, it wasn't very efficient for me to use this tool for scanning large amounts of targets. It quickly dawned on me that in early October, I needed to build a tool that would perform the same exact tests as the tool James created, but in a way that allowed me to decouple it from burp so that I could run it in a headless manner. And also to be developed in such a way where I could provide it with a list of domains for it to run back-to-back scans on overnight. So I wrote a new tool in Python 3 called Smuggler. This tool takes the safe detection methods James discussed and performs it on various desync payloads to the targets that you specify on command line. I took inspiration from dir search on its look and feel. Usually I'm not in favor for writing tools that already exist, but writing this tool allowed me to painfully understand request smuggling at a very low level, so I consider it worth the time and effort. The details on how to use Smuggler and the detection methods it uses will not be discussed in this talk. However, by the time this talk is made public, everyone can go and download Smuggler from my Git repo shown on the slide. Later in the POC section of this talk, I reference CLTE and TECL Turbo Intruder helper scripts. These scripts will also be open source by the time this talk is released. Follow me on Twitter and I should have the links posted there. So a quick note on the impact radius or blast radius of request smuggling desync attacks. When issuing off desync attacks, there's a chance you may affect neighboring connections. The impact of that I split into three categories: open desync, IP desync, and self desync. An open desync is the most dangerous of the three. An attacker issuing a desync attack from any IP address can affect a victim from any other IP address. This is because all requests that come into the front end are funneled down the same connection into the back end. The impact radius of an IP desync is a little bit more limited. In this case, the attacker can only affect neighboring connections from their IP address. This is still dangerous because an attacker can still affect victims behind a common VPN or corporate proxy server. However, a desync attack from one IP address cannot affect web requests from a different IP address. Lastly, a self-desync has the smallest reach of all three categories. It is assumed that for every connection to the front end, there is an associated connection to the back end. Although in this scenario you cannot affect neighboring connections, there is still a security risk. If the front end implements any type of security processing or firewalling, a self-desync can potentially bypass those security checks. If you believe you have request smuggling on a target, use VPNs and VPSs to determine which of the three categories of impact your desync has. Okay, so on to some practical attack recon stories that I've seen throughout my time testing for these issues. Just quick update: these stories are all based on attacks that I've done that have already been resolved and fixed. But I don't have permission from any of the providers' websites to give more detail. So everything is sort of redacted and made up, but the techniques are still valid. So for this specific attack recon story, I had found a TE.cl desync on a main.com server of a major website. But it wasn't looking really good because the impact reach for this TE.cl desync was only a self desync. So I couldn't desync anyone else, and I couldn't desync anyone else on my IP address. I really can only desync my connection. So I sort of had this vulnerability, lying around for a while because it was kind of fairly low impact. At some point, I went back to it, and I decided to look at it a little bit more. And I looked at the robots.txt file of that site, and I looked at some of the endpoints it showed, and one of the endpoints sort of stood out from the rest. And these names are sort of made up. There's one endpoint that was called control room. And I thought that was okay. That's a weird endpoint. What's actually there? And so when I actually did an access through the repeater, the front end reported back that okay, this endpoint was not found. And at this point, I'm not sure why I tried this, but I tried accessing that endpoint through a TE.cl desync bypass. And so with example.com as an example of the payload. The payload roughly looks something like this. We have sort of our transfer encoding malformed header. We have a content length 4 that just encompasses the chunked encoding length, and the rest of the payload sort of gets split as its own request directly into the backend. And when I issued this request and desynced myself to get to the control room endpoint on the backend, I was surprised to see that I got a 200 OK back from the request, and some information that looked like an administration panel that had access to load balancers and cache servers and all sort of this sort of these maintenance control knobs for the main website. So once I reported that, it got triaged and resolved immediately. And the takeaway for this is definitely check your robots.txt file for any weird endpoints, and search for those endpoints bypassing the front end. You never know when the front end is acting as sort of a security barrier, blocking specific endpoints. So it's good to try it out. And even if you have something like a self desync and a TECL, which typically doesn't show much security impact, sometimes you can actually get some pretty high impact from it. So another desync attack recon story. Again, completely fabricated, but the technique is based on a report that I had filed. I had a desync on an API server asset for a major high traffic provider. The vulnerability was a CLTE desync, and the impact reach was an open desync, so I could hijack theoretically any connection that went to the API server. This API server was was primarily used by their mobile app, and so I went immediately to reverse engineering the mobile app, removing the cert pinning restrictions, and getting traffic going through burp to analyze what type of requests are sent to the API server. Immediately, what caught my interest was a request like this that was destined to an authorized user endpoint. This allowed an account owner to add another user as an account owner to their account. And so the schema looked like this. It's a JSON application JSON encoded encoded structure where you specify the user ID, you specify permissions owner, and you just send it off with your session key, and you've authorized that user. And so I played around with this in the repeater, and I found that if you take those parameters and you add it to the request line, even though it's a post, you could actually have the application accept it even at a higher priority than the JSON encoded parameters. So this was immediately useful because typically in a desync attack, you don't have access to changing the body of data on a post request, but you do have access to changing the request endpoint. And if you could change the request endpoint, you could also specify request parameterization on the request line. So immediately I started to create an attack payload for a desync, and in my prefix to be prepended onto a victim request, I added this post line to authorize user with the user ID, my user ID, with permissions owner, and I sent it about 1, 2, 3 times, and was happy to see that I got email notification that I was added as owner to a random user account on the website. So the takeaway from this is if you have a CLTE open desync, sure, it's on its own is already a high priority issue. You could report it as is, but I always like to try and escalate to see what else can I do with it. Can I actually get account access? Can I steal a session token? Can I do those sorts of things? To understand the application, study the API. Go ahead and reverse engineer the mobile app. Try to run it through burp. Figure out what does the protocol and the API look like. And then 3, like I did in this specific instance, if the parameters are JSON encoded, try and see if the application accepts the parameterization via the request line in different forms. You might be surprised to see that even though the mobile app doesn't issue out parameters in that way, that the application actually does accept it, and that could be extremely helpful for desync attacks. And then sort of as a bonus to this, and this is on a completely different report, I did something similar on the request line where most GraphQL targets get data posted to the GraphQL endpoint as post data. But if you read the GraphQL specification, you could actually send GraphQL commands via a GET request on the request line like this. You basically have to set the GraphQL endpoint with a query parameter and then add your query. So I was able to show impact exploiting a GraphQL command that allowed me to do a very sensitive operation on one specific asset. and it allowed me to escalate the report to critical. So for the last desync attack recon story, this attack actually is a third way to obtain a session token. The first two ways are covered in the two POCs at the end of this talk. This one's a little bit more complicated, so I didn't create a POC out of it, but it is a third way to obtain a session token. So I had a main.com asset for a major website, and the vulnerability was a CLTE desync with an impact reach of an open desync, so it was a fairly serious issue. And but there was no useful APIs on the server to the point where I could show any sort of significant impact. And there was no open redirect or response queue poisoning that I could do to steal a session token like I'll be showing in the POCs. So I had to figure out a different way based on the application on how I could steal a session token. So I started playing around with the website through burp like I did with the previous story. And I noticed an interesting endpoint that allows you to invite someone onto your platform. And it was a post to utils invite with a content type of application JSON, and there's two fields. There's an email field where the invite email gets sent to, and there's a name field where you can place a name in the email to who it's addressed to. And so I started playing with this, and I started testing. Okay, well, is there any length limitations to the name field? And there didn't seem to be any sort of restrictions on how much you can put into the name parameter. And so, like the previous story, I decided to figure out, well, could you actually switch this to a URL encoded parameters and obtain the same behavior? And so I did that, and I converted the JSON to URL encoded parameters, and was happy to see that I still received the email at invitee at some.email. So that immediately piqued my interest because there's another type of attack you can perform that is similar to a CLT hijack, but instead of hijacking the victim's request to send them to a different endpoint, you hijack a victim's request to steal their entire request that's sent to the server. And we do that using this type of desync attack, where in this case our desync payload, smuggling payload, is a request, a delete request to the util.example.com server with a character for transfer encoding malformed chunked header that will confuse the front and back end servers. And in the prefix, usually we just specify the endpoint to which we want to send the victim to with a custom header to delete their endpoint. But in this case, what we're doing is we're specifying the entire request for the victim. And in that request, we specify a specific request to the application invite endpoint using the attacker authentication token with the email field already assigned, that is under the attacker's control, but the payload stopping right at the name field. And you can see what will happen is when this payload goes to the front end server, it will parse this entire web request, forward it to the back end server, and the back end server will process the delete request and then process the post request as a separate request. And when it goes to parse the URL encoded fields, the name field will actually contain the entire victim request that was supposed to go to the back end. And with a content length of 500, that puts the parsing deep into the victim request that'll get attached to the name field. So if this attack is done correctly, invitee at some.email will have a name field that will look like an HTTP request. And to my surprise, it did. And so the email that was sent to me at this email address was dear, and then the HTTP request of the victim. And the key thing here is you have to specify a content length long enough so that you are able to grab enough of the request to be able to steal the X app token or the token that's used by the victim. And that's completely pasted right into the email that's sent to the attacker. I've used this successfully on 2 different reports to steal a session token from a victim. And so the takeaway for this is, again, if you have a CLTE open desync, try to escalate. Even if you have no useful APIs and there's no other way to steal a session token, there might be a way to do it in-band to the application of the asset. And so to that end, look for requests that allow you to reflect parameters back to the attacker in a stored manner. It doesn't really help you if it reflects it back in the response because you don't have access to the response at that point. But if you're able to store it in back to the attacker in some way, either through an email or through some sort of field that is associated with the attacker session, that you can later go and look and see what information was stored in that field. You may have the victim's token that is stored in the web request. And then third, yeah, if requests are JSON encoded, just try switching them to URL encoded, because a URL encoded body is useful for this exact type of attack in which you could potentially steal the entire victim's web request. Okay, time to go into demo mode now. These next 2 POCs I've used successfully in over 10 reports to either steal session tokens or private data. To show these techniques, I've developed a couple of CTF examples to illustrate how I typically approach these techniques in practice. For these POCs, I have a server with a load balancer front end pointed to by ctf.reconfig.io. I also have simulated traffic being sent to the server to play the part of the victim. The backend is a gunicorn/Flask framework that was modified by me to introduce a request smuggling vulnerability. This first POC is a very trivial one and is the first thing I look for when I know that a server is vulnerable to CLTE hijacking on any victim connection. After I prove that a server has an open desync issue, I usually directory search it right away looking for 301 or 302 redirects. However, the key is that the redirect should be an absolute redirect instead of a relative redirect. The reason why is that the URL specified in the absolute redirect may be able to be influenced by smuggling specific requests past the front-end server. In the case of a relative redirect, there is very little one can do to influence the redirect away from the server. However, sometimes it can be done depending on the backend. If you are familiar with the request smuggling bug I recently disclosed on Slack's backend to steal session cookies, that report is a prime example of session stealing using an open redirect. I'd like to thank the Slack security team for allowing that disclosure in full unredacted form, as I believe it helped a lot of others understand the impact and severity of this attack. So let's get into it. Okay, so here's the CTF landing page with a couple of hints to scan for a common CTLT style of desync attack. So we use the smuggler tool to search for common forced desync payloads. We find that an underscore payload causes a potential desync issue. So we go and we paste the request into a repeater tab, and we see the landing page successfully. So then we get a common desync payload to robots.txt, and we send it several times until we hijack our own connection and get back the robots.txt content. So next, we go back into the terminal and we do a directory brute force search on the server. We do this to search for any 301 or 302 redirects that may exist on the server, because this could be a potential way to create a forced open redirect to victim connections. So we find that CSS has one. And so we test it and try to desync our own connection to see that the redirection payload. We find that we can redirect our own connection to reconfig.io /css/. So what I usually do here is I see, well, if we provide a full URL to the backend server, to like say x.com, will that actually be, will the backend reflect that back into 301 or 302? And so we send this a couple of times until we see the response from the server. And indeed, the server does actually respond back to x.com /css/. So from here, what we do is we set up a request bin, and we get the URL for that request bin, and we place that URL into the payload, replacing the x.com, and we use this to potentially redirect any other connections to our request bin. So let's see if there are any other requests that we can hijack other than ours. So we send it, and all of a sudden we start to get requests being placed into our request bin. So let's take a look at them. So when we look at them, we look at the headers, we see that, oh, we're actually forcing a redirect from reconfig CTF bot, which is our script that's automatically sending these requests to the server. And so in this request is this xreconfig auth token that has our flag for the conclusion of this CTF. Now, sometimes you may or may not get cookies, depending on whether or not the client or hijacking places those cookies into the requests. But what oftentimes I see is when you have a desync, say an API server, oftentimes you get these auth tokens that are in custom headers that seem to always be there on any request to the API server. So API servers are especially vulnerable to this style of attack, to be able to steal the auth token away from a neighboring victim connection. And so we take the flag here, we bring it back to the landing page, we enter it, and solve the CTF challenge. So let's go over what typically happens in some infrastructures when you send a request that contains a full URL in the request line. Oftentimes, the front-end server will normalize these requests by converting the absolute request URL to a relative request and place the server address in the host header. This acts as sort of a security sanitation because it means that the back-end server will never see an absolute request specified on the request line. However, if an attacker were to bypass the sanitation by smuggling an absolute request directly to the backend server, then this could allow the attacker more control over specifying an open redirect location, say to x.com. In this diagram, the attacker has poisoned the request queue with an absolute request to a foreign server, but an endpoint that the backend server knows to redirect. So with the poison placed, the CTF bot accesses the server with its auth token. CTF bot's request is then merged with the poison, as shown here. And the backend blindly uses the absolute request line as a new server when replying back with a 302 redirect. Assuming the attacker has visibility or control of x.com, then CTF bot will repost all its secret headers back onto a request destined to x.com, where the attacker will use to collect this information. So for the final POC of this talk, I introduced session stealing using response queue poisoning. This attack I found during my desync research is by far the most dangerous attack I've encountered, far more dangerous than CLTE hijacking, and I'll show you why. For this demo, I show a video of me attacking my server ctf.reconfig.io while simulated victim traffic is also being sent to that server. So if you recall, a normal CLTE hijack shown here introduces a poison that sits on the backend TCP connection between the front end and the backend to be prepended to the next web request. This happens because the poison is not a full HTTP request, and so the backend queues the data waiting for the request's conclusion. However, What if instead of a partial HTTP request, the attacker smuggled a full HTTP request? This causes HTTP request splitting, and the backend interprets this one request as two requests, and two responses are generated. So what happens when two responses are generated? Presumably the first response goes back to the attacker, but what does the load balancer do when with their second response? Let's jump into the POC demo. So here's a POC demo of response queue poisoning. First, we scan for some common CLT attacks, which I've done prior. We found an underjoin exploit issue. We have no redirect to exploit this time, and we have a hint to exploit the response queue of the server. So we open a new repeater tab, and we test the connection to the server. So we take the URL to the server, we paste it into the repeater to test that the connection works. We then take a payload of a normal CLT hijack to robots to see if our hijack works. And if we send it a couple times, we see that we do get the robots.txt output. So in this next step, we go into the turbo intruder, where I have a special script to help out with request smuggling and response queue poisoning attacks. I paste in the CLT version of this request smuggling script, and we have a whole bunch of parameters to fill out for this attack. So we first start by specifying the server, ctf.reconfig.io on port 80. We specify an attack count of 3 with regular requests 10, so that we have 13 requests in total. And we continuously send those requests at 10 connections with 5 requests per connection. We specify what our smuggle gadget is. In this case, it's underjoin, so we put an underscore between transfer and encoding. We have a post request, and we specify the host header and the smuggle request as ctf.reconfig.io. For the prefix parameter, we keep it as a get request to 404, a normal 404 not found. We place ctf.reconfig.io as the prefix host, and we specify this as non-chopped, meaning a full HTTP request. We remove any response filters, and we start issuing off to attack. So immediately we start to see regular 200 OKs from the normal landing page, which is typical, and we also see in the response 404s to not found, which means that our smuggles also have worked. But let's take a look at the data closely by filtering out the greetings page. So we add greetings, the string greetings, as our filter to filter out responses that have the word greetings in it. And we just get the 404s, which is the desync reply back. But is there anything else there? Are we confusing the load balancer in any way? For this, we take the string in the 404 not found, and we place it also as a filter. And we see how many requests will it take to confuse the load balancer. And so we start sending hundreds and hundreds of requests, and we start seeing weird responses coming back. Let's take a look, and we see this interesting response that was never requested by the attacker. We have PII data with first name, last name, address, phone number, and social security number, and we have a session token. So we take the session token and we finish the CTF by placing that session token into the main landing page. Okay, so what's happening here? Why did we get a response that was not destined for us? To understand why, let's quickly review how load balancers and other reverse proxies keep track of response order. When you have a load balancer that supports HTTP pipelining, serving many connections, the order of these connections are done as first come, first serve, or first in, first out ordering. In this diagram, we see customer A, B, C, and D sending requests in that order. These requests go down a common backend connection in that order. The responses produced by the backend are sent back in that same order, and the load balancer sends responses back to the requesters also in that order. But what happens if we desync the servers to cause a request split on the back end? This time, customer A is an attacker sending a desync payload with a full HTTP request, and customer B, C, and D are sending normal requests. These requests are sent down the backend connection in that order. However, request A causes an HTTP request split. So how does this affect the response queue? So now, instead of 4, we have 5 responses being sent back from the backend server. The load balancer sends response A back to the attacker, but then response A split is sent to customer B, and the response for customer B is sent to customer C, and the response for customer C is sent to customer D, and so on. If an attacker plays the role of both customer A and customer D, then they have successfully stolen a response intended for customer C, which could contain a session cookie or PII. However, in doing so, the attacker created a lot of collateral damage to the server. Every connection is now getting responses to other connections for the lifetime of the backend connection. So I've used this technique to get critical on several programs. One in particular gave a very generous bounty, but also a stern warning shown here. The biggest problem is in the payload that injects extra HTTP requests into TCP stream. If you are lucky, you'll be able to get a response of their customer's request and his session cookie. Unfortunately, there's a side effect. Every request in this TCP stream from now on will be desynchronized. That means that the next customer's request will get a response to a normal attacker's request, and so on, for as long as the backend TCP connection is open. The result of the above is that not only you are possibly getting the session of some victim, but other people can also get sessions and data which do not belong to them. In other words, a bunch of random people will suddenly receive in the background data that was meant for someone else, and in some cases even valid session cookies, causing them to be suddenly relogged in as someone else. We think it's pretty obvious that when this happens in a production environment, it's not great. Note, this is not a theoretical issue, and in fact we can confirm based on exhaustive analysis of our service logs that this has indeed happened because of your testing. So it goes without saying that response queue poisoning is a very dangerous attack, but can be used by attackers to leak sensitive PII data and session cookies for high throughput, high traffic servers. So that's all I had for today. Thanks everyone for listening to my talk. I hope it gave some inspiration to this weird bug class. I would like to personally thank NahamCon hosts NahamSec, the Cybermentor, Stoke, and John Hammond. And I thank you to all the speakers and sponsors involved in making NahamCon a success. For any blog postings related to my POCs, you can find me on Twitter at DevParam. Also, check out my GitHub account for my latest smuggler tool. Hackers and security teams are free to use it to scan their allowed infrastructures. This tool only points out potential HTTP desync issues, but does not exploit them. For exploitation, check out my Turbo Intruders desync attack helper scripts. Triagers are familiar with these scripts. I've used them to craft payloads to actively exploit desync issues. They are great to use as POC in reproduction steps for request smuggling vulnerability reports. Well, that's it. Thanks everyone. Take care.